Hello guys, so welcome back to our last part of lecture 14. This is basically the end of the rectification. So our last step now with our best circuit full wave rectifier, we're gonna add our last touch, this capacitor, the filtering capacitor or the peak capacitor or the smoothing capacitor that will reduce the variation, too high. It will make the variation too small, we can say. Okay, so the output of the full wave rectifier without a capacitor will be this dashed, red, output here. Okay, but then when we add the capacitor, I will not repeat the analysis with you. So basically, again, from 0 to that point, the capacitor, the diodes D1 and D2 will be off. Okay, this basically, or D3 and D4, I'm sorry, will be off. Then when the input reaches 1.4, not 0.7 this time, the capacitor will charge. So it will follow that curve in here. Okay, until it reaches Vmax minus 1.4. If we are using the constant voltage model, if we are using the ideal model, it will be from 0, from that point, to just Vmax. Okay, and after that point, all the diodes will be just off. Okay, all the time except at that point. Okay, then it will start on again, then off, then on, and so on. Okay, so basically the same output as I'm sorry, it's the same concept as the half wave rectifier with also the smoothing capacitor. Also, we can say now which is better, and we can compare them just on this graph. In the half wave rectifier with the smoothing capacitor, okay, this dome here, this part of the sine wave was not there, so it will just continue this charging like this. So this charging will free from that point in time to that point in time. And of course, the difference between that point and that point is higher than the difference between that point and that point. It's really, smaller than this one. Okay, that's why the full wave rectifier with the smoothing capacitor is much better than, it's basically the standard circuit. This circuit in here, which is just the bridge rectifier with the smoothing capacitor, is the standard. You can consider it as a standard circuit. Whenever you think about designing a good rectifier, you think about this one. Okay, let's now again analyze the ripples. So we quantify or we determine if the rectifier with the smoothing capacitor is good or bad based on the V ripple peak to peak, because this is a peak, this maximum here, which is Vmax minus 1.4, and the other peak is the minimum one, this one is the point at which we stop this charging and again start charging again. Okay, so let's remove all such chaos here and make it clear for you. So variable will be basically between that point, again Vmax minus 1.4, and that point, which we will call V1. Okay, so the difference, which is really small, this is called the VR or variable. Okay, so variable now in full wave rectifier with the smoothing capacitor is equal to Vmax, which is Vmax minus 1.4 minus V1. Okay, good. So what is V1 is basically that. So this is the charge voltage. Okay, so again I'm gonna remind you that it's charge voltage, Vc of t, if this is V initial, and this is from the previous lecture or recording, we discovered that Vc of t while it's charging equal to Vi 1 minus t over Rc. In that case here, R is RL and C is C1. Just the naming for it. Okay, good. So This is the function of time. So determine V1. V1 is Vc of t when t equal to, let's determine it. If we consider this as 0, and this is basically our 0 time here, the start of the discharge, let's call this the distance between that point and that point t dash. So this, it's equal to V1 is equal to Vc when t is equal to t dash. Okay, and remember again, we usually choose RC much larger than t, which is the distance or the period of the sine wave. So this is t, this is t over 2, and this is t, the distance in time between that point and that point. Okay, and based on that, t dash is much equal to, or approximately, I'm sorry, equal to this time t over 2, not t. So here, this is if we consider this as 0, so the distance between that one and that point is t over 2, not t. The distance between that, let's here it's more clear, from that point to that point. This is t over 2. Okay, so approximately equal to Vc when t equal to t over 2. Okay, so Vr, full wave rectifier, equal to Vmax minus 1.4 minus V1 is Vc when t is equal to t over 2. So this will be Vi 1 minus t over 2 Rc. And remember, Vi is the starting voltage when the discharge start, which is this discharge start here. This is the point at which we start discharging. So the Vi is Vm minus 1 over 4. So Vi is Vm minus 1 over 4. I'm sorry, 1.4. So Vm minus 1.4 times 1 minus t over 2 Rc. So Vm minus 1.4 minus Vm minus 1.4. I can just distribute that or the parentheses here. So plus Vm minus 1.4, 1 minus t over 2 Rc, sorry, t over 2 Rc. Okay, this will go with this. So variable in the full wave of the full wave rectifier equal to Vm minus 1.4 t over 2 Rc. T is equal to 1 over f, is a frequency of the input. So variable full wave rectifier equal to Vm minus 1.4 over f 2f Rc. Let's now ignore the 1.4. So, and this is a fair assumption because Vm is usually very high. If the input is a standard input, which come from the standard outlet in your home, it will be around 155. So it's much greater than 1.4. So if Vm is much greater than 1.4, so variable full wave rectifier will be Vm over 2FRC. Let's compare that to the one we get from the half wave rectifier. So in half wave rectifier with smoothing filter, variable was Vm. Again, if we neglect the 0.7 to Vm, because the numerator here was Vm minus 0.7 over FRC. So basically, if we compare these together, we will find that variable in the case of full wave rectifier with a smoothing filter is actually, it's less than this guy, less than variable half wave rectifier with a smoothing filter. It's actually half of it, 50%. And that's good. I mean, remember, variable is a measure for the variation in the output. And remember, our major goal or our ultimate goal is to gain a signal that is completely DC. Okay, so we need this ribbon to be very small. We need this distance between this max and this point, which is just the end of the VV1. We need it to be very small. Okay, so we need the rebel peak to be very small, and that's basically the case in the follow rectifier. So the follow rectifier has half of the rebel of the half of rectifier, which is good. Okay, so that's another aspect why the follow rectifier is much better than the half of rectifier. Okay, so that's basically that's it for the rectifiers, guys. We're gonna start, but we still our ultimate goal hasn't been achieved yet. So our ultimate goal is to gain a constant DC, very perfect DC. Okay, still one minor modification that we're gonna study in the next lecture. Okay, in which if we add to this circuit, we're gonna get a perfect DC. Okay, which is the addition of the Zener diode. So Zener diode is another type of diodes that we're gonna discuss in the next lecture. Our next lecture will be basically the last lecture in diodes. Okay, in which we're gonna study the Zener diode and also its application in such follow rectifiers to get perfect DCs. And when we make this modification and add the Zener diode, we will get what's called voltage regulator or DC regulator. So this Zener will act as a DC regulator. It will regulate our variation to just constant, voltage. It will change this variation, this small variation, this small rebel into a perfect constant voltage. Thank you very much, guys, for watching this video and this lecture, and see you in the next lecture. Bye-bye.